Hi, this is me AbdallahSaad from Egypt. I hope I were with you now in Valencia, but unfortunately I couldn't do it. However, at least my voice and work could do it. I am representing my paper titled Performance Modeling of MPI-based Applications on Cloud Multi-Core Servers. The presentation agenda consists of the following: the problem statement, some hints about the literature, the proposed solution, the experiments tested, the experiments themselves, the results with some analysis, and finally I will conclude and talk about the upcoming future work. Now let's start with the problem statement. The cloud computing nowadays attracts several businesses to move on its flexible, easy-to-use, relatively cheaper platform. High-performance computing is one of these businesses. But several challenges slow down this move. The cloud unpredictable environment is one of these key challenges. We are trying to reduce this unpredictability through modeling the cloud while running high-performance computing applications. Let's give a quick view over the literature. The research on this area is divided into three main categories. The first category is the viability research, where researchers examine the feasibility to run high-performance computing on the cloud via analysis the execution of several high-performance computing benchmarks on the cloud and comparing the performance of high-performance computing different service providers. Their work concludes that the cloud is not recommended for high-performance computing tightly coupled applications because of the slow network interfaces used in the cloud infrastructure, the cloud unpredictable performance for long-run programs, and the heterogeneous infrastructure used in the cloud. The second category of research is the performance optimization research that tries to optimize both the infrastructure and the resource management. Our work is under this category, and in this paper we compare our work with one of the state-of-the-art work in this category, which titled the Program Scalability Analysis for High-Performance Computing Cloud by Shi et al. In their work, they used Amdahl's law with Gustafson's law to model the parallel program scalability. They used the NASA parallel benchmark as a workload. And finally, the third research category is the usability research. It is used in their work. They used to abstract away the cloud infrastructure from the users and tries to move the legacy application into SaaS deployments. Okay, now I will talk about the proposed solution. The proposed solution based on modeling the cloud infrastructure while running tightly coupled MPI-based high-performance computing programs in order to predict its execution time priorly, given some profiling data about the running programs and some info about the cloud underlying resources. The proposed model is the integration of two submodels, the running program model and the underlying cloud system model. To model the running workload, we consider it as a long sequence of infrastructure running on n processes. Each process is repeatedly invoked to perform a number of instructions representing the computation time, followed by a send-receive operation representing the communication time. In the underlying system model, we consider each CPU and network interface as a queue in a closed queuing network. Then we solve the model equations. The model equations is described in detail in the paper. We solve them to get the service time and visit ratio to each queue. Finally, the system response time is calculated using any numerical solution. For example, we used the mean value analysis algorithm, and it was very efficient. This response time is used to calculate the predicted running time of the parallel program on the cloud, based on our model equations. This figure represents our closed queuing network system for modeling the execution of an MPI program on a cluster of K multi-core machines. The figure shows the queuing network for two arbitrary nodes, I and J. All other nodes on the cluster have the same structure. All nodes share a centralized job pool, where the job represents a single invocation of a process. Initially, jobs resides in an MPI jobs pool, which is a collection of jobs ready for execution. A job enters the system through the import and eventually exits through the output and returns back to the pool, completing a job execution life cycle. Then immediately the job rescheduled for another execution cycle, and this process repeats. During the job life cycle, the job is distributed over one of the K processes of the K processing nodes. For instance, node I. The job starts using the processing power of node I through CPU IQ to perform its computation sequence of instruction. After that, the job begins a communication operation with another corresponding job located either locally on node I or remotely on different processing node, for instance, node J. The local communication operation are performed on the CPU queue as a communication overhead quanta, whereas the remote communication operation are done through the processing nodes network queues for the two communicating nodes, for instance, node I and node J. Okay, I am gonna describe now the experiments test bed. In our experiments, we used 8 compute nodes forming an MPI cluster. We use them with 3 different configurations. 2 nodes as a tiny homogeneous cluster, 4 nodes as a homogeneous cluster, and we use them all as 8 nodes heterogeneous cluster. The compute nodes have Intel Xeon processors with the specs shown in that table. The compute nodes have 2 different interfaces used, 2 different network interfaces: Gigabit Ethernet and InfiniBand Network QDR. The workload used in the experiments are 2 benchmarks from SPEC MPI 2007 suite, Lambus and Socorro, and 2 kernels from NASA parallel benchmark suits, CG and MG, with class C as an input size. Now the experiments performed. We have 2 experiments that have been done. The first was to measure the model accuracy over different sizes cluster with 2 SPECS MPI benchmarks by comparing the predicted execution time of each benchmark with the ground truth measured execution time. The second experiment was performed as a comparison with the state-of-the-art scalability analysis method. For the sake of fairness, their work was re-implemented on our testbed, and we use 2 of the NASA parallel benchmarks that they already used. Here are the results and analysis. This is the result of running Socorro and Lambus benchmarks on a cluster of 2 machines. Lambus is in red color and Socorro is in black color. The solid lines represent the measured execution time, where the dashed line represents our prediction. The x-axis represents the number of running processes in parallel to execute the same workload. And we have 2 vertical y-axes. The primary y-axis is for the time in second for Lambus benchmark, and the secondary y-axis is for time in second also, but for Socorro benchmark. We can easily notice how our model prediction cope with the actual measurements. Here, the results shown is for the running Lambus and Socorro on a cluster of 4 machines. Our model is still coping with the actual measurements for both of the benchmarks. Now on a cluster of 8 machines, and we can still cope with the actual measurements, maybe with some errors, but we still coping with high accuracy. We will talk about that now. Okay, for the first experiment now, the model achieves around 90% accuracy for Socorro with 0.16 coefficient of variation, and 82% accuracy for Lambus with 0.24 coefficient of variation. The accuracy here is calculated using the following equation: accuracy equal 100% minus mean absolute percentage error. This is the result for the second experiment, where we compare our model with the scalability analysis model. We can notice that both models are achieving close accuracy before and at 8 running processes. But exceeding this, the scalability analysis model's accuracy degrades, where our model preserves same level of accuracy. Both methods achieves accuracy around 88% for up to 8 processing nodes running, 8 processes running. After that, the scalability analysis model degrades to 61%, where our method preserves the average accuracy on 86%. That is happened because in their methods they consider only for a single process per server, which is a waste of resources and not a typical case. Where our model considered for the intra-communication operation happened due to local communications between processes located on the same servers. Finally, we concluding our work and saying something about the upcoming future work. We have introduced an analytical performance model for predicting the performance of a high-performance computing MPI-based application on the cloud bare metal multi-core server that is proposed. The model considers the contention on both computation and communication resources through modeling them as a queuing network. The model accounts for heterogeneity in the cloud bare metal servers, and we consider 2 benchmarks from SPIC MPI suite, and 2 kernels from NASA parallel benchmark suites. The results show a prediction with accuracy, average accuracy 86%. For the upcoming work, the model can potentially be used in developing better schedulers, and we are now studying the effect of virtualization on the model prediction accuracy. More benchmarks needed to be explored, and we are now working on that. شكرا جزيلا. Many thanks for your kind listening. Domo arigato gozaimashita. Muchas gracias por su atención. Thank you.